Via. Ok. And now we switch to English.
Ok,
Ok,
sto registrando, quindi ottimo.
perfetto. Adesso vediamo se arriva qualcuno.
Ah, penso che Lorenzo sia la borsista.
E non so se dobbiamo accettarli. Ok, perfetto, stanno entrando. Per confermo, tu vedi qualcuno collegato? Io vedo 6 partecipanti, ma non vedo in galleria.
Io sì, vedo quattro spettatori.
Ok, perfetto.
Adesso cerco di mettere la borsista, anche lei come relatore, almeno può rispondere.
Ok, perfetto.
Teoria, ho provato, vediamo se funziona. Ok,
Ok, sì. Ciao.
perfetto,
Ciao.
ciao.
Ok, funziona tutto, perfetto.
Ciao, dottor.
Ok.
I think that maybe we can switch to English already. I don't know how many people are connected. I see that we are 8. So we start and we welcome everybody that's connected now. And maybe we can wait some minutes to wait other people to connect, the late one. And I can share in the meanwhile. Well, first, I'm Manuela. I'm the, let's say, the host of the webinar. I will talk to you about physics. And in the meanwhile, while we wait for other people joining, we can share, let's say, the video of architecture, um, a brief introduction to the course of architecture in PoliTo. So I will switch off my microphone and share the video with you. Okay, I think maybe we can wait just some minutes. In the meanwhile, I think I asked the two girls, Veva and Lorenza, which are here, and they are students, and they will help me in this presentation. They have very good knowledge of all the procedures and information for entering in the course of architecture. So for sure, if you have any question during this webinar, any question you want to do to me or any question you want to do to them, it's more than welcome, because this webinar is for you. So feel really free to ask whatever it comes to your mind. I would like to start by asking to the people that join, if they want, to turn off the microphone and maybe saying the let's say the not the degree, the diploma or the kind of high school that they will come from. And if you want, you can also write it in the chat so that we can understand more or less what's your, let's say, background, and how that's useful also to how to share with you some information depending on what you studied about technical math subjects before, let's say, having the diploma. So yes, please feel free, write in the chat or turn off the microphone and just share with us the place where you come from. Don't feel shy. Or I will ask the girls to call you by name and one by one pick you and ask your provenience. Yeah, as I see that there's a little bit of shyness all about. So that we can start then.
I don't think
Okay.
they can habilitate their microphone,
The
so they
microphone,
probably just
but
can.
if they can write in the chat, I think they can.
Maybe we have to allow them to, because
no, they can. They can.
they can. Okay.
I think if they cannot, I'm sorry, with some organization problem, but theoretically they can. But okay, so if you are too shy, let's just jump in the subject without no more waiting. I will share with you this brief presentation about how you will find physics in the course of architecture. Okay, let's see it together. Sveva and Lorenza, can you confirm that you can see the presentation?
Yes.
Yes.
Perfect. Okay, thank you so much. Okay, if you like physics, have you ever thought about studying architecture? So first, I want to introduce you to let's say, the path that brings us to here, that it's a path of Politecnico di Torino to share information with students, not just in the days of, let's say, the so-called Salone dell'Orientamento, so the event in which people are present in Torino, in Politecnico, and share information about the degree, but also our tentative is to bring information toward the year with these online courses. You can see now today is the day of physics, but there will be a lesson about mathematics on the 26th of May. So if you want some information or are you worried you are worried about that, you can for sure connect and also follow this information. And also this, let's say, lesson talk will be recorded, so you can maybe share it with, if you have friends that are interested in understanding and having information, you can share it with them. And we can, well, first I will present myself. I'm Manuela Baracani. I did classical studies at my high school. I just introduced myself to let you know that studying architecture is possible even if you come from very different background and you have not a really, let's say, linear path and walk inside your studying educative path. Because yes, I studied classical studies in the high school. Then I took the bachelor and master degree in architecture, and then I shift to energy. So let's say a more technical study, and I did my PhD in energy. And so, I mean, that means that really you can become passionate about this kind of subject, even when coming from a very, very different origin, let's say. And let's start with a little bit about talking about Politecnico. Politecnico is a technical school, a technical university. So for sure, if you are thinking about enrolling in Politecnico, you must be aware that you will meet many technical subjects, more than in other degree of architecture that you will find in Italy. Because between all the architecture degree of Italy, Politecnico is really, let's say, push a little bit more on technical and scientific subjects. But this is why. We start from this belief that architecture is knowledge, art, creativity, reasoning, but it's also a technical science that's really needed to make sustainable, conscious, and smart choices when you are designing things. It's not just a matter of taking decision based on your thoughts, on what you like, etc., but it's really taking decision based on reasonable technical data, let's say. And this to make spaces that really are comfortable with people, are safe, and have a low environmental impact, which in the, let's say, last years is something that's becoming really important for the world, and so also for architecture. And technical subjects in PoliTo. The study plans includes mathematics, morphology and structural design, so structures, technology, building physics, material science. And all these subjects are, as you can read, grounded in the physics that maybe some of you studied in high school. In Italy, there are some high school paths that include physics, 2 years, 1 year, 3 years. There are other paths which does not include physics at all. So I don't know if your, let's say, original high school path include technical subjects like that, but we will say, and I can tell you now, that even if you didn't study physics in high school, there's the possibility to start from zero. Every technical subject in PoliTo starts from zero. And so you have the possibility to learn from zero. For sure, you will have to study, and you will have to study more and do a little bit more of fatigue than the people that study physics in high school. But there's the possibility to enroll in the program without, let's say, big problems in the path. But so how physics is connected to architecture? We will see in this brief presentation of today some insights that will show us the connection, but There are many, many, many more that I could not include in this presentation because it will take me hours. But the more you study, the more you discover that really physics and science is really, really linked to architecture. Today we will see just two topics: architecture and structures, which is very related to the laws of mechanics in physics, and architecture and building physics, which is strongly related to thermodynamics and then all other kind of, let's say, study. And so let's start. And we start with structures. That's something that probably all of us can relate to architecture. We know that if we have to build something, we must be aware of how we are building it, and we must be sure that's safe, that's stable, that it can last in the years. So, technical subjects. What's related to mechanical? Here I listed some questions that during my studies of architecture, let's say, I found, I came to my mind, or the teacher that told me the subject make them came to my mind. And that's on very different things, like 16th century citadels with sloped walls. That's something that's related to physics. And why stained glass became fashionable in Gothic cathedral. And before there was no stained glass at all. And then from one certain point in the history, the cathedrals became really tall and with big glasses. Or why the difference of arch, the shape of the arch in architecture bring to a really different aesthetic in the building. So from rounded arch to pointed arch, there is a total different way of approaching the building. And how the architects managed to build a skyscraper of 1 kilometer of height. That's all questions that are related to mechanics and structures. And today we will just see a few of them. But if you are a curious person and you will decide to enroll in architecture, you will discover many of them during your, let's say, your path in the subject. Let's start with arcs. And that's really related to the physics of vectors. When we talk about buildings, our skin against the external condition. We live inside an environment and we should be protected from what's happening inside. Would it be rain? Would it be the colder? Will it be the wind? Will it be the snow or earthquakes or whatever? Buildings are our skin, our protection toward the side. And external loads, static and dynamic, so basically the forces, the impulse that we receive from the outside could really be impactful to our skin. Here, just 3 examples: wind, earthquakes, snow loads. These are all described by physical phenomena, and we will not get in deep in that, but that's just for introduce how physics is related to that. And there is not just external loads, but there are also internal loads. Our skin, our building should resist not just only towards the external wind, snow, rain, earthquakes, whatever it comes from the exterior, but also from how it's built inside. So basically, internal loads, the self-load, that's the building own weight. So let's explore some historical view on structures and loads. Arcs. If we look at the history of architecture from thousands of years, humans, and let's not call architects, but any human that should build something, would it be a house, would it be a temple or whatever, used let's say a shape, structure, morphological, well chosen path. That was the post and lintels. So pillars and something that's staying over the top, the beam. To create openings, we have opaque walls and we should create openings, and the, let's say, simple thing to do is the post and lintel. These thousands of years, from 12,000 before Christ toward now, still we do things like that. And then a new technology came. That was invented from the Roman, and that was the arch. And that was needed because the Romans had to build very, very long and very massive infrastructures, and they needed something that helped them to do so. And this form, this shape that completely transformed architecture, it's working just for the physics of vectors. And now we will see how. So we said that first there was lintel, post and lintels. And what's happening when you have a post and lintels? You have a dipped weight that is, let's say, posed on your material, and you have the pillars that sustain the weight, but in the center you have nothing. So this means that you are really, really stressed. You have to resist to something really, let's say, with high weight. And since they use stone or bricks or things like this, the only way to resist to these loads coming from the building was to do something very thick and heavy, so very, very high. And that's a way in which architecture was formed. Like if we see in the photo, the temples, the very high beam that stay on the pillars, it's not just a matter of aesthetic, but it's a matter of necessity. We need very high beams to be able to sustain the weight. Then what happened? That Romans, as we saw before, invented the round arch that changed the face architecture from that moment on, because Romans, and then going ahead in the history, Romanic architecture start to build tall buildings. Why? How was that possible? For the distribution of vectors. Because if we put the same weight on a rounded arch, the first arch that was, let's say, brought into architecture, the distribution of the forces that follows the three-dimensional vectors, that's a law, let's say, of mechanics, the basic law of mechanics, in which a force can be, let's say, composed on three directions in the space. And so the weight that was on the arch was all unloaded toward this form, because the arch allowed, as you see in the scheme, the weight to be unloaded in a longest direction. That's the blue arrow in the scheme. You had much more material that could resist to the load, because you were going in a diagonal direction instead of going, as in the post and lintel, in a normal perpendicular direction to the material. But what's happening? That having this diagonal direction, we have also the red arrow. That's the horizontal component of the load. The horizontal component just means that this weight will be unloaded vertically, diagonally, but also in an horizontal way. And so we need something to resist to this horizontal unloading of the weight. And that's the reason why, even in this kind of architecture, you always find large, lateral, massive walls. this was need to sustain and to be against the horizontal component of the forces. And having, if you have to, let's say, consider thick walls, that's a limit to our architecture, because if we know that we can do just a few of openings, we will have always something in the corner of the openings, and we cannot go so high because the material has a high weight, and so we can, for structural reason, we can go on very, very, very high building. And then the story went ahead, and another type of arch was invented in the medieval period, and that was the pointed arch. What was the strength of the pointed arch? That while the rounded arch is made from a half of a circle, so really equilibrated, but very, let's say, with squared dimension, the pointed arch is much more vertical, and so the diagonal line of our strength, our vectors, is much, much more inclinated. And so this means that we have much more material, again, in which we can unload our weight. And so this means that if we, as we see in the scheme, the red arrow, the horizontal component, is much, much lower. And so this means that we can have very light walls, very thin walls on the sides of our arch. And that's the shift in architecture that brought to very tall windows, very tall glazed apertures, and very tall buildings. And that's all the medieval Gothical cathedral and with very high space environments, and very high also towers for the bells, and etc. etc. That's a physical, let's say, a law of physics, knowing the law of physics that allows to change a form and to reach a different aesthetical view in architecture. And that's not just aesthetical, because with bigger openings, you can let light goes inside your building, and that changes totally even the feeling, the living of the environment. And so we see posts and lintels from thousands and thousands and thousands of years ago until now, and probably forever. Round arch, invented around the third century before Christ, and more or less the major use of this kind of arch ended in the 16th century after Christ. Pointed arch, invented in the 12th century after Christ, and more or less massive use ended in the 19th century. And that, can we still invent something, other type of form? Yes, we can. And that's what happened in the 17th, 18th century with, 18th, 19th century, with two men. That's, let's say, very interesting. These two men were Gaudí and Robert Hooke, that more or less in the same period invented the catenary arch. What's the catenary arch? Basically, you take a chain and you take the chain from the two, let's say, extreme sides of your chain, and it will take a shape that's totally natural to discharge, to unload the tension inside the chain. That's something that's the perfect shape to unload tensions. What Robert Hooke and Anthony Gaudí, in two different types of world, in two different places of the world, thought, it was that if this was the perfect shape to unload the tensions, could work even in the other direction. So they took the chain and they mirrored the chain and they invented the catenary arch. And they create a new type of architecture with this, because probably Gaudí is the most famous, let's say, example in this topic. But you really visit the buildings and the parks that Gaudí created, and you really feel in a different type of architecture, in a different type of world, something that's totally different from the traditional or modern type of construction and building. And yeah, basically, Gaudí designed the Sagrada Familia with hanging chains. You can see in this photo, which is quite ugly because I did it, but I think it's, let's say, it explains a lot. This is a photo made to a mirror. We are not looking at a model, 3D model. We are looking at a mirror. And over the mirror, on the top, that's not shown in the photo, there are all these hanging chains. These are chains hanged to the ceiling. And they form shapes that this was made from Gaudí. It was a model from Gaudí. These shapes, he used them to realize the real architecture mirrored. And so let's sum up. Structural design. Structural design allows a building to absorb external and internal stresses without suffering damage. And that's a point which an architect should know. And it's not only, let's say, about shapes, what to use and to be technical, but the technical choices bring to creativity. And you can see, I selected some photos here from an engineer from Turin, that's Pierluigi Nervi, which realized a lot of beautiful architectures in the north of Italy. And he really was designing with structures. He used structures to create spaces which, I don't know, I really love the first photo, which has a really impressive and gives also an aesthetical big significance, let's say, big value, aesthetical value to the building. And that's from structures. And so, what will you find in PoliTo, if you can? You will find some courses. First, architecture degree, the morphology and structural design, in which you will approach the basics of structures, theoretical and technical foundations of structures. You will study vectors, equilibrium law, force and distributions, and statics. And this course is the beginning to, let's say, to understand that to build a good architecture, you have to know and form ideas in a harmonic way with the laws of physics. Then, second year, you can apply to a construction atelier, in which, so the design unit, that lasts 6 months, in which you will design things. And you will design residential buildings, mainly, using load-bearing system in concrete, steel, and wood. Also, you can choose another design unit if you want to, let's say, deepen your knowledge about these subjects. And you can choose the restoration and structures atelier on the third year. That's not obligatory, let's see, compulsory, but you can select it if you want. And you will apply the structural design and calculation to restoration of historical buildings. And let's say, what about this admission test? Because if you are thinking about architect going and applying, enrolling in architecture, probably you know that you have to pass an admission test to enter in this. This admission test, I will present something related to the admission test of the last years, not of this year, because every year it is changing, So you can be updated on the changing of this test on the MUIR site, but also follow the, let's say, all the channels of orienteering of PoliTo, and you can have information about that. And so let's see what in the last test, and I will repeat again, these are the tests of the latest year, but we don't know how will be the test of this year. So you need, let's say, to be a little bit proactive and to search information about tests. In the test, you will have some questions related to structures and mechanics. Here I took exactly a question from the architecture admission test of 2017. And let's read it together, just to do an example. It's a question related to the momentum. So a specific, let's say, subject, a specific topic of physics, which is usually part of the high school studies of physics, in particular the mechanics physics. So even if you are thinking about enrolling and doing the test, you can study this type of, let's say, topics on just simply buying a book of high school with physics and mechanics, and starting to study and do exercises on this type of book. In this case, we can read the question. A child with a mass of 20 kilos is moving at a speed of 18 kilometers per hour on a sled with a mass of 5 kilos. That's really Christmas, let's say, question. What is the total momentum of this child sled system? And we have some answers. Let's start before talking about technical, let's say, technical knowledge and formulas and things like that. Let's start to notice something, and I will give you some hints to see and check the how to approach a problem like that. The question can require a specific knowledge in the test, or in last year it was like that. But also you can start to understand and go by, let's say, how can I say, deleting deleting answers that cannot be by simple reasoning. In this case, we have different units in the answers. We need to have just a little bit of knowledge that what the momentum is, that momentum is the product of the mass and velocity of an object. So it means that if I throw a stone in the air, this stone, depending on its mass and on its velocity, will have a momentum. Higher the mass, higher the velocity, higher the momentum. If we just remember this definition, so mass by velocity, we can start to think about the measurement units, because mass is for sure measured in kilos, velocity in meter by second, per second. And so we can already see that in the answers, not all the answers have this type of measurement units. And we can just start to delete the answer which has the wrong measurement units, just remembering the formula, the definition, let's say. Then, if we remember the formula, we can go and do calculations. So we have 20 kilos of child and 5 kilos of sled, the mass, 20 plus 5 kilos. That's moving at 18 kilometers per hour, the velocity. But be aware that to the velocity, we may measure it in meters per second. not kilometers per hour. So to do our, let's say, calculation, we should transform this kilometer by hour in meter per second. And we can do it simply multiplying to go from kilometers to meters, multiplying by 1000, and to go from hour to second, dividing by 3600, because in 1 hour there is 60 minutes, in 1 minute there is 60 seconds, so 60 by 60 is 3600. And so that's our answer, 5 meters by second per second. And if we go substituting, doing the calculation, we will have the answer that's 125 kilo per meter per second. Let's say that if you search for the past admission test, you will find some that are publicly available. This one is one of them. And you can find all the answer in the first position. So you will have a list of questions and all the answers are A answers. So in this case, we can see 125 kilos by meter per second. Okay, I will just drink a little bit of water before going ahead. Sorry. And now we can go ahead with architecture and thermodynamics, so the building physics. That's the, let's say, the subject which I studied when I was doing my PhD. And so here are some other questions related, in this case, to thermodynamics. And again, related to very different, let's say, topics. Like we start from the beautiful windows, carved windows of the Middle East. That's why they were created. That's a reason related to thermodynamics. Or this other, which is really, let's say, I'm really passionate about this because when I was young and I did my swimming courses, I suffered a lot. Why it feels so cold in the swimming pool? And that's probably, maybe men doesn't suffer this, but often women do suffer of this. Or other questions. Why the car windshields, that's the, let's say, frontal glazing of the car, freeze more than the side one? And maybe if you come from a very cold region, you could notice this, or you will notice this next winter. Usually, when you look at cars, you find that the frontal windshield has a major depth of ice when it's cold than the side one. Why? The reason is related to the laws of thermodynamics. How do the wind towers work? And how, maybe you have been in a glazed old building. In Italy, we have some from the 70s, 80s, all glazed. And you go inside and it's super hot. And then we look and we see that all the buildings that are, let's say, the more technological advanced are all glazed. How is it possible? How is it possible that all these skyscrapers does not become greenhouses in which you suffer and it's super hot and you cannot breathe? Always related to thermodynamics. So let's go and let's start from another, let's say, I try to find some example which basically were really fascinating to me and maybe not the very, very common thing that one can think about when we talk about architecture and physics. So transparent water walls, the physics of materials. If you will choose to study architecture in Torino, you must be prepared to the hot summer days in which you will have 32 degrees inside your house and 34, 36 degrees outside your house. And maybe you come from a very hot country and you say, oh, but 32 or 34 is nothing. But it's very humid in Turin. So it's seems nothing, but it feels much, let's say. So 32 degree, 34 degree outside, and you wish to be in the seaside. Why you wish to be in the seaside? Why seaside is more comfortable? For sure, because you are in vacation, then there is wind, and the water is cool. Let's start from this and say, okay, why the water of the sea is cool? Usually we study this in the high school, or when we were more even younger in middle school. We study that the sea, the water of the sea, is cool, even in summer, because water has a high heat capacity. That means the heat capacity of a body is the amount of heat that you must supply to it to raise its temperature of 1 Kelvin. It's a physical property that says that if you have a high heat capacity, you need to supply much heat to make to the let's say your material switch of 1 degree of temperature. And so this means that if you have a big mass of water with high heat capacity, you need a lot of heat to warm it up, and if not heat, you need time, because it's a big mass, and if you have a stable amount of heat, that's the 32, 34 degree that you should give to the seaside, you will need time and time and time to let the seaside warm up. And another thing, if you will come to study in Torino, you will see that while walking in the city in the hot summer days, if you pass over the bridges of the river, suddenly you feel fresh. Why? Why is that? Always for heat capacity and other things that you will see. So if I have a large mass of water, I'll need a lot of energy or a lot of time to heat it up. And that's another interesting thing. You know that the light and the energy, the thermal energy that we see, is something that can be shown in a chart, because it's something that's distributed on different wavelengths, they call it. We see the visible wavelengths. Colors are some specific wavelengths. We don't see the ultraviolet and the infrared. That's outside our visible. But when the sun warms our planet, it is giving us energy, both in visible, in UV, and in infrared. Something that's really nice about water, it's that water is opaque to the infrared energy. What does this mean? The infrared energy is the energy that is related to thermal energy. Why? Because it has certain wavelengths that are more or less in the same range of the chemical bonds of the molecule. So it means that if your molecule are hit by infrared light, they are, let's say, they go exciting because they vibrate, they resonate with the energy, and so they are augmenting their kinetic energy. That's another, let's say, property. Basically, this is just to say, if you have infrared energy, it means that you have heat, thermal energy. The water, you can see in the chart here that the water is very visible, has very high transmission, so it lets pass all the energy of the visible. So basically it's transparent, because in water we can perfectly see, if it's clear, what's on the other side. But it's not transparent, it's totally opaque to the thermal energy. It stops the thermal energy. And so if water blocks infrared radiation, it prevents whatever is behind it from heating up. And so let's come back to our house in Turin, in which I have 32 degrees inside. would it be possible to have a water wall that is transparent to light and that's not letting the energy and the heat go inside the building? Yes, it's possible. It's something that the researcher that wanted to have a little bit of fun created and tested. I had also the possibility to test it in Politecnico with water walls. That means that are walls in which the water is flowing inside. And by flowing, by laminating the wall, it stops the heat, let's say the thermal infrared radiation to pass, and also it cools down by another type of, let's say, work, another type of phenomena, all the system. And does it work? Is this a good idea? Well, on this there are, let's say, different opinions, but it works. You see, I just put the two charts from the experiment I did in PoliTo. You see two lines, the red line and the blue line. Let's just say that the blue line is this glazing that you see in the schema with water that's running inside, and it's able to lower the temperature from 15 to 20 degrees in the glazing. So this means that really it can make a huge difference on what you say. And shall we use just water to do this? No. We find the very similar phenomena also in the traditional houses that we see all around us. For example, old houses in the mountains have thick walls in stone, and they remain very fresh even during hot summer days. Why? Always for heat capacity, and in this case, let's talk about specific heat capacity, which is same thing of heat capacity, but we are not just talking about increasing the temperature of 1 degree, but we are increasing a certain mass of material of 1 degree. So this means that if I have 1 kilo of material, I will need some heat. If I have 10 kilos of material, for sure, I will need much more heat to warm it up. The stone mountains houses combine very big thickness of the wall, so large mass. We have many kilos of material, and high specific heat, because the specific heat capacity, because the stone is a material that has high specific heat capacity. And so this is the reason why the hot, the energy, the heat is not able to pass inside my building. It passes with a very high time lag, and it's really attenuated. And one can have a fresh house even in summer. And so shall we build houses in stone as let's say, thousands of years ago? No, because if you know the laws of physics, the law of materials, you are able to reach the exact same result with very different materials. And let's say not building in stone, but with very thinner dimension. And exactly, modern buildings, the passive houses, etc., can delay the passage of the heat of 12 or 16 hours. That means that if you had midday, you have 38 degrees, you will feel the effect of this 38 degrees in midnight, when the outside temperature usually is lower. And also they reduce all the heat transmission, the losing of energy beside the walls. And that's one reason why studying the materials and knowing the physics helps to do architecture, because you can have a comfortable environment using much less material and with very less complex let's say, construction ways than building a house in stones. For sure, stone is heavy. Stone is very difficult material to work with. Stone requires such a precision in the putting the walls one around the other. Instead, you can reach even better results with different materials. Oops. Let's come back to one of the things we see, we said before, walking on the Po River. We said, and I really advise you to try, if you have a river next to your house, to try in summer to walk beside or over it, and you will to feel that's very, very cool in comparison to the temperature of the neighborhood. And why is this so? Again, laws of physics, temperature and evaporation phenomena. The water temperature is low for the reasons that we see before. First, it has an initial temperature that's very low, between 6 degrees in let's say winter and up to 15 degrees in the plains of the let's say the fields, plain fields. If you find a source of water underground, that's the maximum temperature, no more than 15. And why is that? Because the water has an enormous heat capacity and it ran in the ground for very, very long time and long distance, and it exchanged the heat with the ground that also has a very high heat capacity, and so the sun does not warm up the ground. And so it reached a constant temperature, and it exits to this temperature. And then, again, high heat capacity. It exits from the ground at maximum 15 degrees, and even when it exits, it does not warm up because it needs a lot of heat to warm up, okay? And second reason, evaporation. That's really cool. In the water, the molecules that have higher kinetic energy, the thermal energy we saw before, are excited, and they are liquid, they are excited, they come to an internal kinetic energy to a level that's the one that make them evaporate. So this means that they go ahead, they fly away, they evaporate, and they do a phase change, a passage of phase. And to do the passage of phase, they need energy. And so they absorb energy from the air. And so basically we feel cool because the water evaporating is absorbing the heat from the air. And also this, let's say, evaporation, it makes an exchange of mass in the air, and so it creates air currents, and so the pleasant wind that we feel when we walk on the river, it's related to this. And so, I am an architect. Can I exploit evaporation processes in the design of my building? So we talk about all this stuff and you say, what does it mean? How does it relate to architecture? Okay, let's talk about this. Are there architects that exploit the evaporation processes in the design? And for sure they are, starting from, let's say, again, history, the water games. You will find many castles with water games in which the objective was, yes, to have something that was fun, okay, but really to pass hot summer days with the help of water. So making people wet, but also with pools and fountains that were continuing this evaporation process and to cool down all the architecture with this. And still, modern architects are doing this more than, let's say, more frequently in the north of Europe, where there is a higher attention, as always, to, let's say, environmental issues. But many architects are using this type of design, making pools, making big water storages in the plaza, etc. This is an example, the Museum of History of Trento, and that's a photo of a playground in New York, in which, if you look at the photo in the right, that are very ugly, still because I did it, there are again water games. So in summer, while in winter it's like in the central photo, everything dry. In summer, there are pools and fountains which help to cool down the temperature. And again, we can go ahead in this and push much more than this, because if we let's say, pay attention to the phenomena of, let's say, the destructive phenomena, environmental phenomena, which happens in the cities now, we know that, let's say, torrential rains are some destructive phenomena. But we can exploit the strength of the torrential rains by collecting the water and transform this huge amount of water that comes all in once to something that can mitigate the urban heat island. Again, doing pools, etc., etc., etc. And that's an example very nice of Rotterdam. I left some links if you want to check it, in which they create a system that collects all the rain from the roofs and it pushes it through tanks, internal tanks, and when it rains, the water fill up the plaza. So this plaza that now you can see as a colored dry plaza becomes a lake. And that helps mitigating the urban heat island and preventing the torrential rains to make damage to the city. Apart of, for sure, giving water to trees and being, let's say, creating a reserve of water for plants and grass. Last topic, then I promise I will end with talking about thermodynamics. And that's heat transfer. Does it burn or does it not burn? So, again, if you studied physics in high school, you studied that the heat, the energy, heat in specific, is transferred in three ways. Conduction in solid, so like if you touch a hot pot, you feel the heat. Convection in fluids, that's the reason why you dry your hair with the phone. And radiation, so like if you stay in front of in a fireplace, you will feel the big hot radiation that's coming. And radiation go in any medium, and that's related to temperature, and we can see it better later. So how does relate this? Is that related to buildings? For sure, buildings will act and react to heat waves or heat flux with these three physical phenomena: conduction, convection, and radiation. For conduction, let's say that the major way in which we can relate this passage of heat in buildings is hot surfaces. In this case, it's not a building, it's a closed environment in which people live, the car, and all the studies of modern science about heating up the seating of the seats of the car is related to passing heat through conduction. Convection, basically anything. When you have something that's a surface that's hot, for sure you will have convection around here, because the, let's say, a fluid, that can be air or water or whatever, that touch a hot surface, heats up and then move away. For the same reason why, let's say, that we all know that hot air go toward the up direction, the vertical direction. Convection does exactly this thing. So radiators, fan coils, whatever, it works for convection. Radiation the frontier now of, let's say, systems to heat up, to climatize the houses, radiant panels. So it's something in which a hot fluid or a cool fluid goes inside, and that's heating or cooling down the environment. Really, really interesting. And we are talking here, if you see, we talk almost always of systems, building system. And so one can ask, do I control heat transfer only through mechanical system? The radiators, the fan coils, the hot surfaces? No, for sure. The envelope is a fundamental element for energy saving and comfort. Again, the heated, in restoration, as you cannot put mechanical system like in churches or temples or things like that, they started to put hot surfaces to warm people from conduction. Convection. In any building, the control of ventilation and air movement is totally related to energy expenses and comfort of the people inside. Radiation cools surfaces. We will go and check a little more deep this topic. But first, convection. Yeah, exactly. We said that one of the questions at the beginning was skyscrapers. How can I do a skyscraper without making it become a greenhouse in which you die for heat? Basically, you work with a specific technology. That's the double skin facade. That's quite similar of what we saw with water in the transparent walled waters before. You have a window, you have a fluid that's going inside, and that's air in this case. And while going, this cool fluid laminates the hot glazing of the window and takes the heat away. And that's the only way in which a skyscraper can be built without having problems of energy and of comfort in the people inside. If you will see a modern skyscraper, maybe in the, let's say, Middle East places in which, lucky them, they don't have problem of energy now, maybe there is still something that does not work with this, but if there is, it's very low. There is a small amount, let's say. All the other use the double skin facade technology. So all the other skyscraper that you see around have this invisible air layer that it's running through their skin to cool them down. What about radiation? That's another, let's say, topic which I'm passionate of. It depends on the surfaces and the temperature surfaces. The surface is temperature. And again, the swimming pool. I remember when I did my swimming course, I was always dying of cold while waiting to jump inside the water. But the regulations require that swimming pool have a temperature of 22 degrees. 22 degrees, I mean, probably all of us can stay in t-shirt and feel perfectly nice. So why at this temperature, even if the air temperature is warm, let's say 22 degrees warm, why do we feel so cold in a swimming pool? And that's the same reason, by the way, why the windshield of the car freezes more than the side one. But if you're curious about that, you will search the answer in another place. And that's related to the physics of the black body. Black body physics, what really, let's say briefly, what does it say? All bodies that with a temperature measured than 0 Kelvin emit radiation and absorb radiation. A black body emits and absorbs the maximum radiation it has related to this temperature. Real bodies that are gray bodies emit and absorb a part of the radiation. of the energy. This heat exchange depends on three things: emissivity, position, and absolute temperatures. So, if one of the two bodies that exchange this energy between them is particularly cold, the other cools down as well. Why? Because basically there is one body that is exchanging a lot of heat and is giving heat and giving energy and giving energy, but the other body is not answering not answering to him. So basically, the body that's hot is losing energy without receiving anything back. And that's why in swimming pools you feel so cold, because swimming pools have all glazed, let's say almost all, let's say a big amount of glazed walls all around. And glazing, as we know, it's a not insulating materials. So the temperature of glazing really, really cools down. Normally 5 degrees in winter, but it can go very, very to very lower temperature, even under the zero. And so even if the air temperature inside is 22 degrees, 24 degrees, you are exchanging, you are giving energy all around you without receiving nothing in back. And that's the reason why you feel so cold. So let's sum up again. Choosing material, insulation levels, orientation, the size of the glazed surfaces, all of these have an enormous impact on comfort and energy consumption of the building. And we didn't talk about the sun, but we will leave this for the future of who will do architecture. And so basically, designing intelligently means knowing the physical principle and using them to make harmonious thing, balancing the human needs and the natural processes. The more we know, the best environment we can create. And in PoliTo, you find these materials in different courses. Technology, Culture and Fundamentals of Technology in the first year, in which you see the principle of physics of materials, building elements, construction processes, etc. And then there is the big course that is building physics, second years. That's more or less all one of the, let's say, the hardest, let's say, courses of the path. And here you will study all the principle of macroscopic physics and the practical application to building. So with the exercise, you will really learn to use this principle to create a good environment. And then you will have material science and technology, again, second years, in which you will study the microscopic physics. So all the some concept of chemistry, evaporation, internal tension of materials, durability, etc., etc., etc. And what about the admission test? What we can see in admission test, or at least what we saw in last years, were some questions like that. For example, 50 grams of water at a temperature of 20 degrees are poured into a container that already contains 200 grams of water at a temperature of 70 degrees. What's the final temperature of all the water after the mixing process is complete? And here we should use the thermodynamics basic formula, heat balance equation, in which the heat balance equation says that it's related to the specific heat capacity. Remember that the specific heat was the amount of heat that was needed to warm up of 1 degree a mass of 1 kilo of material, 1 unit of material. And so for the laws of thermodynamics, nothing is destroyed, but everything changes. So if you have a certain amount of energy in your system, this energy should be maintained in the system. It cannot disappear. It will be maintained. And so this means that the sum of the, let's say, the balance of heat should be zero. The balance between the different energy that comes into a system is always zero. The difference of this energy is always zero. And so if we just substitute our data, let's say here we are talking about water in both sides, so we can not consider specific heat because is equal on both sides. We consider 50 grams for mass multiplied by the difference of the temperature of final temperature minus 20 degrees, that's the initial temperature, plus 200 grams multiplied by final temperature minus 70 degrees. And you just do all the calculation, blah, 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 and you've reached the answer 60 degrees. So in this case, you need to know the basic laws of thermodynamics to answer to the question. Other type of question, 200 liters of water in an aquarium. Knowing that the specific heat capacity of water is this 4,186 joules per kilokelvin, what amount of energy is required to increase its temperature by 1 degree? Again, specific heat. And again, you must know the law of the specific heat capacity. So the heat is related to the mass, to the specific heat capacity, the property of the material, and to the temperature difference. You go by substituting the values and you reach the result. And just some notes about how the admission test up to 2025 was organized. You had 5 sections and 1 section had physics and mathematics. 10 questions between physics and mathematics. So you will have multiple choices, blah, blah, blah. So you will need that if you go to do the admission test, there will be at least 10 sections like this. And you can find here the whole test in the, if you search test architectura more, you can find them to have a little bit of, let's say, trial. And I promise we are at the end. In the end, do I really need physics to become an architect? That's something a question that when I was teaching in Politecnico, I received from one of my students. And so basically I would say, yes, you need it. Because we will perfectly know that buildings have an impact on the environment. 30% of global energy consumption is related to buildings. And so reducing the energy consumption of buildings reduce the greenhouse emission and the, let's say, the impact on the environment. But also, these, let's say, consumptions are related to the occupant behavior. If the occupant is in a discomfort condition, it will change the things in the building. It will open the window even if it's winter, or it will close the window if it's summer, or it will heat up turn on the light, etc., etc., etc. And so what we have to do, we have to guarantee the comfort of the people inside the building. And this, to guarantee the comfort, as we saw for the swimming pool and the discomfort of being let's say, exposed to very cool surfaces, we need to know building physics and thermodynamics to solve these problems at the beginning. And here are other things, but I won't go because we are running out of time. But basically, living in a good environment has an impact on concentration, satisfaction, work performance, well-being, and health. So it's really important. It's really valuable to know the physics and to build really well-done houses, well-done, well-functioning houses to guarantee the health and the well-being and the quality of life of people. Also lowering the environmental impact. And yeah, a part of the fact that we'll have many regulations that now in this year obliged you to do so. So basically, that's it. Thanks, and that's it. And if you have any question, please, really feel free. I hope you are still alive and not sleeping too much. Any question about, okay, will I be able to enroll? I did not study physics. Am I able to enroll to this? Or I have a big love for physics and what I saw is not enough. Please, really feel free to make to me any question. I will maybe ask Zveva and Lorenza if they see questions around. Just, just help me to see them. I also open the chat.
Yes, there were some questions, but
Oh, perfect, fantastic.
Lorenzo already answered them about the enrollment process.
Fantastic, fantastic. Thank you.
And in the meanwhile, if we are still waiting for their questions, I ask one question. I know attendance is not required, but can you still pass exams, like physics exams, even if you're not attending classes?
Okay, thank you, Zveva, for the question. Let's say that I think it's an important question because I will say from the beginning the technical subjects in PoliTo are the maybe for many people um, the more difficult one. So basically, it happens a lot that the technical subjects are the last that people have to follow and to do exam with. But this is also due exactly to not, let's say, coming in presence to the lessons. I think it's very important for this type of lessons to be present, to participate to the lesson. For sure, because you can have the chance to understand better. You can do all the questions, and I really advise people to do questions, even if they seem stupid. Never lose the chance to do questions. And also because being in place allows you to follow and to be aware of all the instrumentation that the university gives to pass the exam. You will have exercises, you will have teacher assistant that will guide you doing exercise, doing simulations of the exams. You will have the tutoraggio, which I don't remember the name in English, tutoring, let's say. You will have the chance of follow tutoring classes. And so basically, yes, for sure, if you are good in technical subjects, you can do the exam without being placed, without being present to the lessons. But I think it's a very good opportunity not to be missed to follow in presence all the classes.
Okay, thank you.
So I really would say, please, really feel free to make any question because that's a chance you have, and maybe you will not have soon. You have three people, Sveva, Lorenza, and me, that studied architecture in different moment of the um, of life. So let's say still student. I'm already, let's say, now working in real life as I would say architect slash engineer. And so just feel free.
We have a
Okay,
question
that's
now.
a question for me, I think. Enrollment stage as the first and second phase. When you, the presenter, applied, what phase you were in? Sorry, no, I don't know if it's for me, if it says. Oh, in a sense of how secure did you feel that you would be given a seat? I worried about my admission mark and will make me stand out. I think that maybe on this, I don't know, Sveva, if you are first enrollment or second enrollment.
I did the test a few years ago, so I think I maybe it worked differently. I
Yeah,
remember.
because me, sorry.
Uh, sorry, no, because I think there's the enrollment is like ranking, and I don't think there's like a secure mark upon which you have the spot. For example, it's like this in engineering, or also I think in planning. You need to do more than 60, and you are sure you have the spot. In architecture, it's different because you could even do all the answers wrong in the test and still have the spot. Hypothetical, of course. It's not. It's very unlikely, but you could. So I think it depends also a lot each year. It depends how many people are doing the test and how maybe also the difficulty of the questions, how well they do, and I think every year is different.
If I can give you an advice, I suggest to take some time to prepare for the test because there are some topics like I don't know. Today we look at physics. You can prepare for the admission test and for the questions of physics and mathematics already starting from the a basic high school book of physics and catching the topics which I show you. That's more or less the questions are momentum, equilibrium, heat, this type of questions. So if you are worried about exactly the test, take some time to prepare to the question to the test and question.
Yeah, also take as many last former tests that you can find because they are very similar in structure, and so it's a very good practice. I for preparing my exam, I did a lot of tests, and I think it was probably one of the most useful things that I did.
Yeah, very, very good suggestion. Yeah.
Okay, I think also when you apply on the Apply PoliTo page and you register for the test, I think you're also going to get access to the former tests, so you can do them when you apply and try them all. But also those that you are doing, I think it's very useful. You can try also many types, also because as the professor said, we don't know yet how the test is going to be, so it's good practice.
Okay, still 2 minutes, so last chance for questions. Anything that come to your mind? Also, if you want to leave some comments, for sure. We are happy. I am happy to understand if I make you sleep or if it was a little bit interesting, even because for next years I will manage and balance the content depending on that. I think I have to sum it up a little bit more because it's too much things, but I assure you because it's something which I really love, and that's nice because I mean studying architecture make me love these technical subjects. So who knows? Maybe will be your destiny too. I will just while last minute. I will just add this information. Again, every technical subject start from zero, and Polytechnical gives the possibility also to follow, let's say, this tutoring path for if you have problems in following one specific subject. So you can apply to architecture and study physics, even if you didn't do anything about that before. And if you are passionate about physics, I mean, I'm here saying you can have the possibility to study it more. I choose the thesis in physics, in building physics. That was a very, very good chance to study it. And you can choose technical, let's say, courses that are facultative, and so you can deepen more definitely. But another question, what's really the difference between architecture and civil engineering? I'm applying to both. Let's say that with civil engineering, you have a totally different method of studying. Architecture is then maybe Sveva, if you want to add or correct me, but in my experience, architecture is let's say, subject, a path in which the method is less rigid, let's say, less theoretical, less studied on books, and it's much more on trials and application on real examples, which is all, let's say, good sides and bad sides. If you study engineering, you will start with a very, very strong basis, scientific basis, mathematics, physics, technical materials, informatics. You will have a very strong basis, and you will go, let's say, on more technical things. If you have the passion of designing and composition, so let's say, not just thinking about how mechanically and structurally things are done, but also the, let's say, the concept that's in the base. What story do you want to tell with your buildings? What do you want to pass to the people that are living the building? If you have an approach that's much more, I would say, structured, that's maybe the way you have to go in engineering. And if you instead have an approach which is a little bit, can be much, much more, I won't say creative, maybe yes, creative in some way, but the fact is that it's applied to practical examples. You learn by doing. And that's super different also the fact that in architecture, you will work in teams. So you basically will teach your mind to be elastic. The real difference in which I see between architects and engineers is that engineers have a strong preparation, strong knowledge, architects not. I'm sorry, architects has not a strong knowledge, but they are elastic, so they can approach the problems seeing different sides, doing something that's different from basic and the traditional way of doing things. I don't know if Sveva, you want to add something?
Yes, maybe something on a more practical level. For example, I think engineering in the first year is the same subjects for every engineering course. So if you are interested in something more about topics that are more related to architecture, you are going to need for the second year, because I think there's just one exam that's more related to the kind of engineering that you have chosen. So you are going to have 2 courses of maths, physics, chemistry, informatics. And so I think that's also something that you need to evaluate when you choose, because if you don't really like those subjects, it can be a tough year. And but I think it's also a good idea to apply to both of them, because in architecture, you just have one chance to get in. Engineering, you can redo the tests many times. And so maybe you manage to enter in engineering and not architecture. You can still do your year in engineering, then retry the test, and you can still convert some exams. So you haven't wasted 1 year, and maybe or maybe you will find engineering interesting and you just stay there.
Very good. Thanks, really thanks for the question that are really, really appreciated. Yeah, so I think that's if in this last minute nobody wants to do other questions, I will say that's it. We will end the webinar. So I'm speaking because so the some seconds pass, and if there are a last minute question, it passes, but I don't think so. I really thank every one of you for participating. I hope this was interesting and a little bit showed you, made you understand what's the purpose of doing physics in architecture. And good luck for everything. Good luck if you are the last year. Good luck if you want to try to come to Italy and enroll. And thanks again for the participation. Thanks, Sveva and Lorenza, for assisting me and answering the question. Thank you very much. Bye. Have a good what you do. Bye to everyone.
Bye.